Yes, so thank you, Keith, for the introduction, and I think setting the stage for what I will try to talk about now in the next 29 minutes and 53 seconds. So we'll see how that goes. So as Keith says, Chief Technology, I'm actually the Chief Geophysicist. I'm a geophysicist by trade, not an HPC engineer or anything like that. I've dabbled and used computer throughout my career from graduate school and onwards. And in this presentation, I'm really going to try to walk you through the logic of why we made the step from what I call clusters to supercomputers. And I'll try to define that. I might be way off from my definitions, but that's for you guys to give me some feedback on. But I sort of entered, at least in graduate school years, where we had SGIs, we had CM5 thinking machines, and supercomputers of that time. Then it all pivoted onto these Beowulf clusters or clusters, and they are still used in supercomputing. But I think for us, that was sort of the bread and butter of everything that we have done in the last 15 years, I would say. But we as a company, last year, pivoted around and did something that everyone, or my colleagues on the sort of oil service side, they just stood there and scratched their head and said, you guys are insane. Why are you doing this? It makes no sense, and so on. I think Keith gave away a few hints as to why we have done it, and it was with the scaling, because we deal with problem sizes that get bigger and bigger, and we were running up against the same memory limits that BP or everyone in our business have had. I think we are, unlike BP, using the computers every day in the low margin business. We didn't have the luxury even of the 256 gigs, because they were at the price point where 128 was the where we could be, and that sort of very much limits you to the size of the problems that you can solve. So to try to address the challenge that there's lots of HPC experts in the room, I'll spend a few minutes to talk about what it is that we do in seismic imaging, and this is not a complete treatment of it at all, so there's going to be lots of things we're going to brush over very quickly. But what we do for a living in PGS is we run ships, like you can see here, over the world's oceans to acquire data for oil companies. So we are a service provider in that sense. Imagine these are sort of very large-scale ultrasound machines that are used to make 3D images of the subsurface. So wherever BP or an Exxon or Chevron wants to acquire data, we hope they call us, and then we will bring these guys out and make that data acquisition. We tow behind here some very large sensor arrays. So they are 10 kilometers long, 2 kilometers wide, and you can run constellations of these vessels. So they, we tend to, as an industry, make claims about the world's biggest moving objects and so on in the classic one-up on each other. But fairly massive infrastructure that is pulled through the water to acquire seismic data. And then, as I said here, the HPC enters the scene by taking these sound recordings, so it's basically microphones submerged in water that we're dealing with, and then we are making three-dimensional images. So this is just a slice through one, but an image cube out of all of that data. And from a computer science point of view, this is just a massive data reduction exercise. And I think Keith mentioned data sets in the petabytes. I think of hundreds of terabytes as being quite normal, but no one will ever look at that, or no geologist will ever look at that at the workstation. So that is the data reduction, where you're making an image, and that image will maybe have 3 dimensions, 4 or 5, but that will be greatly reduced so that you can actually work with that as a subsurface image. And this is where HPC has been important. It still is important. You heard Keith saying BP has continued to invest in this. Total is another big investor, Exxon. I mean, everyone in the oil and gas industry have an investment in HPC, I would say. So then a primer on seismic imaging, just to sort of walk you very quickly through the process. So this is what this sound data, or the reflection data, so you set off a source, so that's what you can see has happened up here, and then we record the echoes or the reflections from the subsurface. So maybe for us that call ourselves geophysicists, this makes a bit of sense, but not really. I mean, you have to then actually use this data and run a imaging process with it. So that's, think of ultrasound, it's the same kind of setup. We deal with a much more complex media than medical imaging typically do, because it has large contrast, so it's a strongly scattering media. We don't know the media, it's unknown, so we have to actually derive a velocity model like this. So that's a model of the subsurface from the data itself. But once we have an approximate model, we can solve partial differential equations and create an image of the subsurface in 3D. And that's what the geologists and eventually drillers and so on will understand and use. So I'm sure you will get a refresh of this and the talk that Scott will give and John will give, so I'll run over these things a bit quick. But I think there is one point here that is in terms of the seismic shots, because that is illustrated here in a cartoon way, that this, for us, a boat or on land, you will set off a seismic source, that's an air gun or a dynamite on shore and whatnot, and you record all of the reflections on or in your sensor array. But if you look at one shot as one experiment, in my knowledge of this, that's what gave sort of the birth of this embarrassingly parallel regime that clusters grew into and took over our business, because you could treat each shot as a single experiment. It was a reasonable size. I mean, the time axis here is maybe 10 seconds. You have some hundreds of thousands of sensors, 10 seconds worth of data at a couple of millisecond sampling. You could cram all that into these computers that Keith mentioned, 256 gigs, solve a wave equation and get an image, and then you would concatenate and add all these images together in a composite way for the full surface. So we were able to thrive as an industry and ride for free or for cheap Moore's law and whatnot with this for a very long time. But I think 3 years ago we sort of started to butt up against where things were. And the only other sort of technical detail I'll give as a motivation for why we did what we did is related to the wave equation that we solve for a living, because we made some choices there on the numerics of how we're doing that. So we left the stencil-based methods. We're relying on multidimensional FFTs, and that's another sort of thing where, maybe someone will ask why you're not using accelerators. Okay, FFTs some years back on accelerators, and particularly multidimensional, were not very good. So we are CPU shop as well, but we're solving this, the left-hand side here with multidimensional FFTs. And that's when these things have to scale, and as Keith mentioned, network becomes quite important in this. So I think I've covered most of these things here. Go back one. Keith said it's been linear. I think there's been exponential, because we have demanding clients that want more and more resolution. I mean, I think that is regardless of the price regime that we operate in. And this wonderful PD that we're dealing with has 3 spatial dimensions and a time dimension, so this scales to the frequency of the 4th. And that can basically kill off any memory footprint or any compute capacity that you have. And that is a price, market set expectations on what maximum frequency people want out of the data. But it's a relentless drive, so this will help keep driving the need for more and more flops, maybe also more and more memory. But I think you'll see at my conclusion that we feel, at least for now, for the next couple of years, we are okay with on the memory side. It's how we can get more detail out of the data that's going to really be the next step. So then this is the final slide of my introduction, and just to show again that what we're dealing with here is very inexact. If you're a mathematician, it is adjoint operators. We're not doing inversion. So what I'm showing here is a synthetic model. It is a model based on the Gulf of Mexico. There's a salt body in here, so that is a high contrast, a large contrast in both velocity and density. So it bends the waves and makes shadow zones. So you can see these shadow zones in here. And that is sort of things that we, even with the perfect model, the perfect data, and a seismic imaging algorithm, you cannot resolve, because this is the true reflectivity of that particular model that you're seeing here on the right. And I'll get into at the very end what we are now being able to do with this new hardware that we have available, where we can get to a solution that is much closer to the true reflectivity by doing inversion. So that is sort of one step beyond, again, the cluster-driven imaging that we have been involved in for the last 10, 15 years. So that was 2 minutes on seismic imaging. So now I'm going to try to give a bit of motivation for why PGS did computers a bit differently. And I've given parts of this talk before then to more of an oil and gas audience, and we have a history in PGS, so we were maybe a bit late to this game. I mean, it's a company that's gone through a tremendous growth over the last 10 years. So we actually sat in a funny position that we were late for some things, we were maybe early for some things. We have lots of vessels. We have a sound financial footing to build on still, and that has enabled us to do things different. So we'll see what sort of comes behind there. So I said small market size, so that was sort of, if you're too big, if you have too many customers to serve, it is quite difficult to change. And I think from talking to people at the national labs and whatnot, it's the same thing. My code has all of these users, and we're moving platforms, it becomes a very complex thing. But we're focused, we were smaller than our peers, so we actually were able to then up the game a bit and change out and do things quite different. We also have no software arms, so that is another sort of, I think, dilemma for some of our competitors, because they sell their software commercially, so they have then a massive maintenance operation with that, and to sort of turn around and redesign your software from a platform change naturally would take longer when you have to go through more rigorous quality controls than us that we could afford to do in this particular situation. So this allowed us to do things differently. That's the sum of that. I put in one bullet here to say that we're sticking to the plan. I think it's important that these changes are not ad hoc changes. I mean, we sat down and set ourselves some goals quite some time, 7 years back in time, and we'll come back to that. So this is the plan that we operate by in the part of the company that I work in, and we had a few things that is important financially. So that was grow behind our feet, because we are probably the leading company when it comes to running marine acquisition and ships. So that provided us with a solid foundation. We said we're going to focus not on capturing customers, but improving our productivity. And we said we want to do new things with our customers. So that says we're not going to copy what other people are doing, and it allowed us to go to work and only do a couple of things, not try to do everything that happens in the seismic business. So based on those principles that belong to my boss, this is what I control in the company as a sort of looking after the technology. So we've set up these principles. I think you can sort of see where this is leading. This is where the computer piece comes in, because we said we're going to move towards full wave field processing, and I'll get back to what that is. But that is basically breaking from this embarrassingly parallel regime of treating one shot at a time. I say we acquired a survey, it covers an area of the Earth. You're going to try to treat that as one domain and then make images. So this is getting sort of geophysical technical here, but we have turned the problem a bit upside down, and we say we're going to provide a multi-dimensional image of the subsurface where all the coordinates live in the Earth, not related necessarily to the acquisition domain where the vessels have moved around. So this in here is also where the need for memory, as Keith pointed out, adds in, because a three-dimensional volume is maybe 10 gigabytes or something like that, but we are then producing hundreds of of copies of that, redundant dimensions, so that will again scale the need for memory also on output. We were also, I think, early adapters in terms of saying we want to use inversion, and I'll come back to that. So that it goes away from this adjoint imaging principle and pushes different requirements on computers. Big linear systems, interconnects are important, solvers are important, and so on, and it's a new technology in our business. So then time to market, programming model, I mean, Keith, as I said, he did a great job laying out the challenges that we have. But how can you take things that we really don't know quite how to do in our business yet, or it's new applications? So the theory is easy, but how do you make a proof of concept and get that done quickly and efficiently at scale? So this was, when first I showed these, there was a bit of a sort of showing the dirty laundry of PGS, because the numbers, so there's no scale here, but just as a sort of graph. I mean, we have had exponential growth because we were, as I said, back in 2009, where we sort of sat down and made a strategy for how to grow. We were very small. We did not have critical mass in HPC. We lacked expertise in HPC. But as you can see over time, I mean, this was 2015. I think we bumped up on that one, and we're continuing on that trend. So I think BP has been ahead of us there. They've had a longer history. I think we have done a good job now of catching up, and we'll see if our curve also flattens out as we move forward in time. But the key thing here is to talk about how did we approach this, because we were sitting down here and said we needed to do something. So I also like to put up this one, because that's what has happened to us in the same time, and trust me, to grow a business on an exponential price increase that we've had, and you see in Texas, I think, the impact of high oil price everywhere, but in the middle of this, I mean, we've had some disruptions. We're weathering that storm, but clearly it has had an impact on our ability to do things at will. So where were we with this? We were relying on Linux clusters, not at scale. That was 2010. I'd say right away we missed the GPU wave, or the early wave. That was for us a call on organizational capabilities that, if we don't have our act really together, why jump on something where you have to spend all of your time modifying the codes and whatnot? Clearly you can get performance, but we felt at the time that we had missed the wave on GPU. And many of our competitors have gone heavily into this as their compute platform. So with this, we sort of said, okay, that train might be gone. We need to look for a radically different solution. I'll mention again that this, for us, price performance has been key. So everything, all these decisions have been measured up against, I think, good quality or price control of everything that we do, and not increasing our marginal cost for delivering these services. So it talks about supercomputing. People say, oh, supercomputers are expensive, but here I try to tell a story about that you can adapt those kind of architectures even in a very cost-conscious, low-margin business that we run in. Maybe point number 4 is also, for me, close to heart, and I'm not going to dwell too much on that here today, but the development time to market, I mean, the oil and gas business is often viewed as being stagnant and a bit backward-looking, but I think us, at least as a service provider, we rely on the ability to bring new things to market fast. And my philosophy is that forego IP and control of these things. If you can be out front and lead, that's a better approach to be, but that puts some pressure on the programming model, the infrastructure that you work on, and all of these things. So the first supercomputer that we then went back to, and the PGS that I joined back in 2008, I mean, they had FPGAs, they had GPUs, they had a bit of everything and a few clusters, but we were still only dabbling in computers. So looking around at the landscape, I think Keith mentioned 2 of the competing architectures that we also looked at, Cray and SGI, but we went and procured a small Cray XC30 system. That was like one of these building blocks that they offer up. So there is issues or good things in my mind with the interconnect on these 2 cabinet units. That was like the smallest building block that you could get from Cray in order to try out what they have on offer in terms of the Aries interconnect and so on. Inside the box, and this is something I spent a lot of time explaining to my bosses and our CEO, it's like, it's the same CPU that we could have in our Dell or HP or a more conventional box. So don't have your hopes up that a certain old application is going to run a lot faster on this machine. It is more what you can do with the interconnect and stability, programming model, and so on. So that's what we had to go and pursue. So this has moved on, and I think it took us, I need to remind myself here, but 13, 12, a year and a half to sort of say that, yeah, the bet has paid off in terms of research. Then we much more than doubled down. So this is one row of a computer that's called Abel that sits in Houston in a shared facility. So we are not as lucky as Keith, who has his own beautiful facility, but the computer looks very nice. And the silk screens, we toured the TAC facility here earlier today, and it's just nice to see that computers can be beautiful objects in that sense as well. But that was a 12-fold increase on our Cray side, at least, when this system was installed. And in the next section here, I'll get to the business driver, the lever that we use to be able to defend that investment level in 2015, because we are not doing this with back on pumping oil. We're doing it based on the back end of delivering a service. So this machine went in. These slides are unfortunately a bit old, because actually this year, as we speak, I think 2 weeks ago, we installed another system like this that is now online in Houston. So this bet and the direction where we're staying true to that, and the capacity keeps increasing in terms of that. The generational changes, this is an XC40 system compared to the research system that was XC30, but that's above my head in terms of the intricate differences between those two naming conventions from Cray. So then, how could we grow? How could we defend this growth? Again, as a geophysicist, I'll give you a bit, pictures to show big, wrong direction, big data or data flow. And I like to show these three pictures and say, the big data challenge in seismic. So from before, or Keith was well established in the business at this time, I think, and then 6 of these listening cables, what we could tow. Today we're sitting with a capacity that can tow 24. There's more sensors. The sensors are longer, so they went from maybe being 4 to 5 kilometers long to being 10 kilometers long. So there you have a order of magnitude more data just from the engineering or of an ocean-going vessel and the capacity of that to pull equipment through the water. So that really drives the need to do things in computing. And I hope John will talk about this from a land seismic point of view later on, because the moment you're going to sample this differently and go even finer, you're going to get an exponential growth, because the platforms we have available today in terms of towing this equipment are state of the art, and I think we're only starting to scratch the surface in terms of how much data you actually can acquire. And that comes a lot down to the sources. You might remember that from the previous shot, that those are still very few, or much fewer than the listening devices. So we have 2 sources that are shooting in a sort of a pattern, boom, boom, and we record all of this. But I think 5-10 years from now, there will be a bunch of sources, and that will again just explode the amount of data that we have to handle off these vessels. So this was my little bit of arithmetic, but I think Keith basically talked about it, that if you add this up and compute what what we can record, it is tons of terabytes per day. We have the challenge, so if there are people with ideas on this, that we run 12 of these autonomous boats that are autonomous on the ocean. They acquire enormous amounts of data. One thing is to get it off, but there's also challenges here of how you can hold it, and we are then obligated to keep that data around. So we are backing it up. We do have redundancy in all of those systems, but that is getting more and more expensive as the data volumes increase, obviously. So that has sort of talked you through what we did and why we did it, and we had a plan. We stuck to the plan, and it worked out. And I'll talk now a little bit about what we used as a lever, because we needed some business behind this to actually pay for the expenses. And we went out and acquired some seismic data before that drop in the oil price took place. So that's ironic when you stand here some years after. But for us, that was the biggest data set that we have acquired in terms of data density. I mean, you can acquire more data, but the data density here is enormous. And the problem size was such that we couldn't fit it into a 256 gig footprint in one of the nodes. If we wanted to, process or make an image out of this survey, we had to do something different. That was what sort of the business push behind all of the story that I talked to you guys about here now was based on this survey. You had to go outside the 256 gig footprint, and here's a quick summary of why and how that happened. So this was, I said, a multi-vessel operation. So we looked at what one of these boats can acquire, but here we ran 2 of them at the same time. We also had 5 sources, so that gives you another sort of factor 5 in terms of the data that we had to handle, and that's how we acquired a lot of data in about a year, back and forth to the moon, 3.5 times in equivalent in terms of coverage that we obtained with this survey. So it's big data. It's very different than the word big data, but for us, the data handling and the problem sizes are a real challenge today, and as we move forward. So we did a sort of bar napkin calculus of this. I mean, you see Keith, he has 5,400 nodes, but we needed at least 6,000, knowing that, or assuming that none of them would break, everything would work as it would, add 256 gigs, and then we would barely meet our customers' requirements. So that would basically say the frequency has to be this, and then the problem will fit inside the 256 gig footprint. So Think back to this Cray story that had evolved here in the background. We had tested this. We had built prototype software that left the parallel regime behind, and we went to a distributed FFT-based implementation for solving the wave equation, and this was really put to the test in this survey. So that you know, behind what we ended up doing, this is the picture of the first system that we have is named ABLE after a Norwegian mathematician. There's an ABLE prize for those of you in the field that is also sponsored by PGS. So we managed to spin a good story around this computer as well as we got it in, and good enough that we were given a second one here a couple of weeks back that our CFO inspected yesterday. So he was still, you know, I'm still standing on my 2 feet and no blue eyes. So I think it was a success. That's you never know how that goes. So we busted, in my mind, this, and I think in the next 2 or 3 slides, I'll talk you through how that took place. I think that for you guys as an audience, this is less interesting. Cray has a standout here. They will tell you all about how this machine works. The thing is really the all-to-all communication that we have to use, and you can see that the amount of memory that we have, slightly less than BP, is on the order so you can keep a whole of these surveys in the address space at any point in time. So that will enable you to solve problems differently than what we have done in the past. So I said that we had commodity nodes. You could run a set size or set version of this problem in a commodity node. So that was our benchmark because the flops inside were all the same. There were CPUs. So we then went through, you know, the software programming modules, software modification to be able to run this on the Cray. So if we took the code that we ran on the commodity, and you have here a supercomputer, there's no scratch disk in these nodes, it is an interconnected system, it had a Lustre file system as well. If we took the code as it was, put it on the system, not a good story to tell. And clearly our CFO, he was interested, could you run this more cost effectively? Could you solve that problem more cost effectively with the new system? And as I said, a small group of researchers set to work, and good help from Cray on this as well to sort of teach us how to use this interconnect and adopt some of the software related to the FFTs and transposes. But the end of this story is that when it was all said and done with the same CPU, we were actually able to live up to the brand of a supercomputer and actually solve the problem faster than on a commodity node. So on one node versus using more nodes, and I put that down to not using any scratch, because now all the problem solving is done in memory, whilst the solution here has local disk, RAIDs, whatever that sit in the node. You spew data off and you read it back. But that is the only sort of high-level explanation for why we were able to make it even faster, because now we keep the whole problem in memory at all times. I think I covered one node, one shot, and that was what we moved beyond here. So we have really then transcended this whole embarrassingly parallel regime one time and for all, hopefully. So we will see how that goes. I'm seeing I'm running 2 minutes left there, but I'm going to click through this one pretty quickly. So this was also more fun facts of the size of the problems. I think if you look at this, that what you have generated here with the full data volume that we keep inside the machine, image the size of Texas 5 times to depth of 16 kilometers. So from a geographical imaging exercise, very, very large problems that are being addressed. I'm going to skip these because I have talked too long today. I know they're going to talk a bit what we do with inversion. But now there's the next phase. I said that the imaging has been, adjoint operators is a bit simplified compared to the problems that we're really trying to solve. And so this is the newest addition to what we have been up to, using a tightly coupled, well interconnected system. As I said, new geophysics that we can do. We are moving away from shot-by-shot processing. I'm not going to dwell much on the imaging condition, but when I say you're going to get more than one source at a time, it means that the wave fields become more complex. You're going to have to treat this as continuous data streams that are multidimensional, and that data flow and the data models that you're going to use will really break everything that we have done historically as a business. And I had this little cartoon here just to show that each of these shots historically, they fit very well into an old PC or a fancy cluster like this. But when we then start to put things together into, this is running very slow on this little machine, into a continuous record with multiple sources and lots of recordings, how are you going to treat this in an embarrassingly parallel regime? And that's where we said, okay, this is the platform, or this type of platform is needed to solve these problems in the future. Then I'm going to talk a little bit about inversion and say that this is something that we have moved into, and instead of, I keep pushing the wrong, Instead of only solving this little imaging problem that everything I've shown you today has been about, if you want to do here a formal least square solution to your data problem, you have to solve large linear systems. You see the data sizes. You can imagine that these matrices gets very, very big. I'm just going to show more that what we have done. So we need sparse solvers that are fast. We need to have a system that supports this. These are taking hours and hours, maybe a day or two. So you need infrastructure that's staying up, that is resilient to failure, fault tolerant. I mean, all of these challenges that are common in the domain of HPC. So, yeah, so what can that do in terms of my opening picture here? This was the migrated image, the adjoint. So you can see the shadow zone caused by the large contrast in the media. But when we then move to inversion, we are able to a large degree correct for that and make a much more true representation of the subsurface. There are a couple of clients in here, so I promise I'll show a couple of seismic pictures. So this is from the Gulf of Mexico, so this is field data. It's a pretty large, a couple of 100 square kilometers, but very sizable problem to solve in a computer. And moving from imaging that we have done historically into inversion, this is the kind of resolution improvements that we can obtain with that. I think with that, I'll just jump to my conclusion. You guys can read that, and there might be time for one or two questions if there are. So thanks for your attention, and sorry for running a bit over time. So thank you. Yep.